Okay, so we're going to go over when two principal ideals could possibly be the same and talk a little bit about how a principal ideal could be all of R. So let me motivate this theorem that I'm about to say with an example. Let's scroll all the way up to the tippy top. So when we were doing this MZ example, we noticed something. We noticed here in the note that mz is the same as negative mz. In terms of our principal ideal language, this is saying that m is the same as negative m. And I'm going to choose to write that negative m as negative 1 times m. And so what this is saying is that associates, in this case m and negative m, are associates in z. Associates generate the same principal ideal. The principal ideal stays the same. And so that's the theorem we're going to prove. Let's scroll back down. So theorem, then if A and B are associates, then the principal ideal generated by A, I don't know why it's skipping, principal ideal generated by A is the same as the principal ideal generated by B. Proof. Well, associates. Proof. So suppose A and B are associates. Oh shoot, A and B are in R, sorry. Not just A. Then there exists a unit, U, such that A is a unit times, or let me write it the other way. B is a unit times A. It doesn't matter which way, but I'm going to choose to write it this way. So what we're trying to show is we need to show that every multiple of B is also a multiple of A, and conversely. Okay, so this is just writing out what it means to be associates. So we need to show that every multiple of A is a multiple of B, and every multiple of B is a multiple of A. For the first containment, let's take some multiple of A. So I'm going to write like this. Let's take some RA in the ideal generated by A for some R and R. Then, sorry, I think I also want to write, let me put it under here. This is the same thing as saying A is U inverse B. It's a unit, so the multiplicative inverse exists. We can move it to the other side. Then what RA, I'm going to use what I just wrote here in orange, is RU inverse B, is RU inverse B. Ooh, that became an arrow somehow. And that is a multiple of B. Cool. So RA is in B, so we can conclude that every multiple of A is also a multiple of B. Let's do the backwards direction. So let's take some SB in B, some S in R. Then what? Well, SB, B is UA, right? So that's SUA, and so that's SUA, and that's also a multiple of A. So any element of the principal ideal generated by B is also in the principal ideal generated by A. And so we have our double containment argument. Okay, so if you're associates, you actually generate the same principal ideal. However, it need not be the case that if you generate the same principal ideal that you are associates. At least it's not obvious to me. So this is not this. Let me think for a second, actually. Yeah, I think that in a general ring, if you generate the same principal ideal, you need not be associates. Uh, and the reason is because of the presence of zero divisors. So we won't go down that route, but we are going to point out here that if we're associates, we generate the same principal ideal. And I also want to make a note in the comment I made in the last video. As an example, if U in R times is a unit, what kind of principal ideal does it generate? Well, the principal ideal generated by U has U in it, right? Because U is certainly a multiple of U, it's 1 times U. Well, this tells us then that this guy has a unit, and whenever an ideal has a unit, it's all of R. Okay, so my point here is that sometimes your principal ideals aren't going to be like, they won't necessarily be proper. In particular, the principal ideals generated by a unit are are everything. So they of course aren't proper. They're trivial ideal. So sometimes that happens. And let's also point out one more instance that we saw earlier. The principal ideal generated by 0 is just 0, because all multiples of 0 are 0. So this is another case in which we get a trivial example by looking at a principal ideal generated by something.